Good morning, students. We'll start with the today's lecture. Okay, already we have completed two units, Unit 1 and Unit 2. Today we'll start with Unit 3, right? In the Unit 3, we'll start with the root locus techniques, right? Okay, in the previous chapter, we have seen the stability analysis of a system using Ruth criteria. That Ruth criteria was a mathematical technique in order to judge the stability of the system, right? Okay, in Unit 3, this root locus technique, it is also one of the method to determine the stability of the system, but this is a graphical method, right? It is not a mathematical method, but it is a graphical method in order to judge the stability of the given system. Okay, what are the things we are going to study here? Just the syllabus that is going to be covered in this chapter is the brief introduction to root locus, the root locus concepts, how to construct the root locus, that is construction of root loci, and numerical examples, right? Okay, today we will cover all these things. Introduction to root locus, brief introduction, then something we'll see about angle and magnitude condition, then how to determine the graphical method to determine the value of k, right? Then okay, we'll understand one by one later on. Then rules for the construction of root locus. Yes, there are totally 8 rules are there in order to construct the root locus. After constructing the root locus, we can judge the stability of the system. That we will see one by one slowly, right? Okay, this root locus method, it was developed by the person Mr. W.R. Evans in the year 1948 itself, right? So in the year 1948 by Mr. W.R. Evans is the person who has introduced this graphical method in order to judge the stability of the system. Okay, this is a graphical method, please keep in the mind. Okay, just before telling you something, how the root locus looks like, I'll tell just one example. The root locus, there are several forms. This is how the root locus, this is the root locus here. It starts here. This is the pole here located at -1, 0, and another pole is located at -3. And from this pole, the branch is starting here and it moves in the upward direction like this. I hope you can see it. And another branch, right, it starts from this pole and it moves here like this. And from this pole, this branch is moving, right? And always you can observe the root locus is symmetrical about the real axis. This is the real axis, upper part and lower part, they are symmetrical, right? Okay, we will see how to construct all these things. We will see what is this root. Just I have shown you, this is one example. The root locus, there are different shapes are there. This is one example for particular system. Okay, okay, we'll try to understand. Okay, we know the characteristic equation of any of the closed loop system is given by 1 plus g of s into h of s equal to g. This is the characteristic equation, right? Okay, let us take the closed loop system, right? Closed loop system, you can observe here, this is the forward path transfer function g of s. It has system gain k, g dash of s. For this k into g dash of s is the forward path transfer function. Let me call it as g of s. G of s is equal to k into g dash of s. This both, right, they are in series, right? Okay, this is g of s, forward path transfer function. G of s is nothing but k into g dash of s, right? And feedback path transfer function is h of s. Input is r of s, output is c of s. We know this. So the characteristic equation of the system is, we know that it is 1 plus g of s into h of s equal to 0. What is g of s? It is k into g dash of s. So 1 plus k into g dash of s into h of s equal to 0, right? Okay, this is the characteristic equation. And the value of k can be anything, right? If k is equal to 1, k equal to 2, 3, I will get different sets of characteristic equations. So as the value of k can be varied from minus infinity to plus infinity, right? So means if it is varied from minus infinity, it means I will be getting infinite number of characteristic equations, right, for all those values, right? I hope you are getting. Okay, for particular value of k, let me assume k equal to 1. Okay, I will get one characteristic equation, maybe of second order or third order or fourth order based on the given system, right? I'll solve the roots, right? All those things you know, right? I will get some set of roots or poles, closed loop poles. For k equal to 2, I will get another set of poles or roots. For k equal to 3, I will get another set of roots or poles, closed loop poles, right? Those roots of the characteristic equation are nothing but the closed loop poles of the system. You know it, right? Okay. I hope you are getting. Just let me write it. C of s by r of s. The transfer function I will write g of s divided by 1 plus g of s into h of s. Is it fine? And here g of s is k into g dash of s, you know it, right? Oh, this denominator polynomial we call it as characteristic equation. And the roots of the characteristic equation are nothing but the poles of the closed loop system. I hope you are getting, right? For particular value of k, let me take, I have already told k equal to 1, I will get some set of roots, nothing but the closed loop poles. For k equal to 2, I will get another set of roots or poles for k equal to 3 and so on. K can be varied from minus infinity to plus infinity. By joining the set of closed loop poles, right, we get some locus. That locus we call it as root locus, right, because k can be varied from minus infinity to plus infinity. For particular value of k, I will get some set of poles. For k equal to 1, I will get some set of poles. For k equal to 2, I will get another set of poles. For k equal to 3, another set of poles, and so on. If I join all those set of poles, then root locus, the locus is formed. That locus we call it as root locus. Means the locus obtained by joining the closed loop poles for different values of k. K is the system gain, right? K is the system gain, right? So if k is here, means it will work k into j dash of s, right? K is the system gain. It will be coming in the numerator. Okay. I hope you understood. If k is varied from 0 to infinity, only positive values. If k is varied from minus infinity to 0, right? So 0 to infinity we call it as direct root locus. Direct, just the name. If the value of k is varied from 0 to infinity, only positive values, direct root locus. If k is varied from minus infinity to 0, right, negative values, right? So it is inverse root locus. Please keep in the mind, inverse root locus. Always we think only about direct root locus, means always the k is varied from 0 to infinity. We will not worry about this part, right? So always we assume that k is varied from 0 to infinity. We will see only the direct root locus, not the inverse root locus, right? Okay. Already I have defined what is root locus, right? By joining the set of location of the roots or set of location of the closed loop poles, right? As the value of k is varied from minus infinity to plus infinity, the locus obtained we call it as root locus, right? So here it is defined. So we can define the root locus as the locus of the closed loop poles obtained when system gain k is varied from minus infinity to plus infinity is called the root locus. For example, I have shown you, right? This is the root locus. Okay, there are several things you can observe in this. This is one example, that's all I have taken, general example. The root locus will be different for different systems. This is for one of the system, right? You can see here, the poles are located here at 0, -1, -3. The poles are located. For example, some system is there, right? Okay, you can observe here, from this pole, this branch is moving here. At this point, there are several terms are there. I will introduce those terms slowly. This breakaway point, it is breaking here and it moves in this direction. It moves in this direction towards infinity. This is one branch. Let me change the ink color. You will come to know slowly, one by one. From this branch, from this open loop pole, the branch will, and it will break away at this breakaway point, and it moves in the downward direction symmetrically, right? Okay, another pole is there here at -3. This branch will start here and it moves towards infinity. It moves towards infinity, right? Okay, three branches. I will introduce some terms here for you people, right? So now you came to know branches. I'll tell you one by one. Branches. Then this point is called as breakaway point. Breakaway point. This one, right? Breakaway point. Then poles. Okay, fine. And this point you can observe here. This is the point here, and there is something dotted line goes like this, right? Here one line is there, it is going like this, and here this goes like this. So this we call it as asymptotes. These are the asymptotes, means they are guidelines for the branches. This is the branch which is moving towards infinity like this, but it has to move corresponding to this asymptotes. This is so something new we'll study here. Asymptotes. Just I'll tell you, asymptotes are nothing but the guidelines for the branches which are moving towards infinity. This is one of the branch which is moving towards infinity, and this is the guideline. This guideline will tell move parallel with me, move along this direction, and this guideline is telling for this branch move along with me in this direction, right? One more asymptote is there. It is telling move parallel with me like this, right? Asymptotes are the guidelines for the branches which are moving towards infinity. That we'll see one by one. And this point we call it as centroid. For example, in this -1.3, it is always means where to locate this as, from where, which point I have to draw this asymptotes. That is we call it as centroid. This is centroid, right? So few terms I will introduce you people, right? We'll study one by one, right? Okay. So branches, breakaway point, asymptotes, centroid, all those things we'll study. Just one example, how this root locus, and you can check here, this is the real axis. If I cut it like this, so it is symmetrical, above part and below part, right? The root locus is always symmetrical about the real axis, right? It is mirror image, right? So above part and below part, they are mirror images. So root locus is always symmetrical about the real axis. So just now I told we will be studying some rules in order to construct the root locus. One of the first rule is the root locus is always symmetrical about the real axis. Already without knowing that rule we have studied, the root locus is always symmetrical about the real axis. One by one we will see, right? Okay. And these asymptotes are making some angles here with respect to this theta 1, right? Theta 2, this second asymptote, third asymptote from here, it goes like this, theta 3. So how to calculate angle of asymptotes, how to calculate centroid, all those things we'll study one by one next, right? Okay, this is sufficient. Okay, next, before studying that, already I told what is direct root locus. If the value of k is varied from 0 to infinity, we call it as direct root locus. If the value of k is varied from minus infinity to, we call it as inverse root locus. Always we study only direct root locus. Means always the value of k is varied from 0 to infinity, right? So we concentrate only on direct root locus. If I write RL, it is root locus only, right? RL means root locus. Right, fine. Okay, next we'll study the next topic, that is angle and magnitude condition. That was the brief introduction to root locus. Next we'll study the angle and magnitude. Once again I will tell you one line, one line, that root locus method or technique, it is a graphical method in order to judge the stability of the given system. That we'll see it later, right? How we can judge the stability of the given system by this graph. This is a graphical. I got some graph here, right? I got some graph here. By this graph I can judge the stability of the system, right? Okay, you can see here, for k equal to some value I am getting this roots, for k equal to some other value I will get another set of roots. So by joining all these roots, this will form a branch like this. This is locus obtained by joining all the set of closed loop poles or roots for different values of k. Similarly, this is another locus, right? So this we call it as root locus. Okay, next we'll see the next topic, angle and magnitude condition. So for any general closed loop system, we know the characteristic equation is given by 1 plus g of s and h of s equal to g. This is the characteristic equation. Then g of s and h of, take this one this side, so it is minus 1, right? Okay, s plane is already a complex plane, already I told you. So g of s and h of s, instead of simply writing minus 1, I can write it as minus 1 plus j0, right? Because it has real part and imaginary part is 0, but I told that S plane is a complex plane, so it has real part as well as imaginary part. Imaginary part here it is 0, minus 1 plus j0, right? If I say that for there are several set of values of s, if I give s equal to 1, s equal to 2, whether that satisfies, whether that point lies on the root locus or not, means there are several points are there. By joining all these closed loop poles or set of roots of characteristic equation, this locus is formed, right? So in order to judge for particular value of s whether that point s lies on root locus or not, it has to satisfy this condition, g of s and h of s equal to minus 1 plus j0. So for that there are two conditions, angle condition and magnitude condition, we'll say from this, right? Okay, if I want to say that any particular point lies on the root locus, then it has to satisfy angle condition, right? If it satisfies angle condition, I can say that the point lies on the root locus, right? Then magnitude condition we'll see next. If from this magnitude condition I can find out the value of k, right? And if the point has to be on the root locus before satisfying this magnitude condition. So we'll take up next the angle condition first. First we'll study the angle condition. What is this angle condition? Just now we have seen g of s and h of s is equal to minus 1 plus j0, right? This is the condition. Okay, take angle on both the sides. What is angle condition, right? This already we know, g of s into h of s equal to minus 1 plus j0, right? The same thing I have taken here. Then take angle on both the sides. Angle of, this is the notation for angle, angle of g of s into h of s is equal to odd multiple of 180 degree. Why it is odd multiple, I will tell you. Plus or minus 2q plus 1. Q can take any value, 0, 1, 2. Go on substituting, you will get odd values, 1, 3, 5, 7, 9, like this, right? So I will say plus or minus odd multiple, 2q plus 1, nothing but odd multiple of 180 degree. How I will tell you? Observe here, minus 1 plus j0, the point, this is the s plane, right? Sigma j omega. minus 1 plus j0, minus 1 plus j0, I can look at the point here, right? This is minus 1 plus j0, right? Okay. Always we measure the angle in anti-clockwise direction. If I measure the angle in anti-clockwise direction towards this point, minus 1 plus j0, it is plus 180 degree. If I measure the angle in clockwise direction, it is minus 180 degree. I can measure the angle in anti-clockwise direction or clockwise direction, right? So where this, so angle of this, so angle of g of s and h of s odd multiple of 180 degree. If I from this positive real axis, if I move in the anti-clockwise direction, it makes 180 degree. If I move in the clockwise direction, it makes minus 180 degree, right? So I have written plus or minus 180 degree. Okay. Next, I want to reach this point 180. Next, I have to move 360. 180 plus 360, it is 540. Next angle is plus 180 plus, so you can observe here. So plus 540, I will come once again here. Next 540 plus 360, once again 94, plus 900. Right? I can come in the anti-clockwise direction. If I measure, it is positive. If I measure in the clockwise direction, it is negative. So plus or minus 180 degree, I will reach this point. Plus or minus 540, then also I will reach this point, minus 1 plus j0. Plus or minus 900, I will reach this point, and so on. If you continue, plus or minus odd multiple of 180 degree, right? So substitute q equal to 0, I will get plus or minus 180 degree. Substitute q equal to 1, I will get plus or minus 540. Q equal to 1, right? So 200 to 2 plus 1, 3 into 180, 540. Next, q equal to 2, right? 2 to the 4, 4 plus 1, 5, 5 into 18, 900 degree. So generally I can write, so the angle condition is angle of g of s and h of s is equal to plus or minus 2q plus 1 into 180 degree, where q takes the value 0, 1, 2 and so on. This 2q plus 1 is nothing but odd multiple 1, 3, 5 based on the values of q. I hope you understood how the angle is measured for this point, minus 1 plus j0, right? I hope you are getting. If any doubts, please clarify the doubts as and when it comes to you. So this is the angle condition. Okay, I will give one point s equal to minus 0.5 or minus 0.75, or some complex point also I can give, minus 2 plus or minus plus j2 plus j2, something like this. So whether this point s equal to minus 0.5 lies on the root locus or not, I want to test it. Whether this point s equal to minus 0.75, whether this point s equal to minus 2 plus j2, they lie in the root locus or not. If I want to test, it has to satisfy the angle condition. If I get the, suppose any g of s and h of s open loop transfer function is given to you people, find the angle of that. If it is odd multiple of 180 degree, it satisfies angle condition, and this point, whatever the points that are given, they lie on the root locus. If they does not satisfy, then means if I am not getting odd multiple of 1, if I am getting 200 degree, 240 for example, then it is not odd multiple of 180 degree, it fails to satisfy the angle condition. Hence I will say that that point does not lie on the root locus. Yes, that we'll see. We'll solve numericals based on this, right? So I hope you understood the angle condition. This is the condition, right, for any of the closed loop, open loop g of s minus 1 plus j. From this we have taken angle on both the sides. Next we'll see the magnitude condition. So before going for magnitude condition, we'll solve one numerical, right? Okay, solution is there, but I will not look at the solution. I will go in the next, just only take the question. Consider the system with g of s into h of s. This is g of s into given, that is equal to k divided by s into s plus 2 into s plus 4. Find whether this point s equal to minus 0.75 is on the root locus or not using angle condition. So we will go for the next slide. G of s into h of s is equal to k divided by s into s plus 2, sorry, s into s plus 2 into s plus 4, and we want to check whether this point s equal to minus 0.75 lies on the root locus or not using angle condition. Okay, fine. What is angle condition? We will write first angle condition. Angle of g of s into h of s is equal to plus or minus odd multiple 2q plus 1 into 180 degree. This is the angle condition, right? So angle condition. So if this point s equal to minus 0.75, I want to test whether this point lies on root locus or not. If it lies on the root locus, means then it has to satisfy angle condition. Let us see whether this point satisfies angle condition or not, right? So this is g of s and h of s. Let me apply angle on both the sides. So angle of g of s into h of s is equal to angle of k, angle of k. Simply instead of writing, just I will write plus j0. It doesn't affect anything, no. Imaginary part anyhow it is 0 because I want to, because S plane is a complex domain, right? Let me write it like this, no problem. So angle of S plus 2. I am applying, splitting the angle for numerator, angle for denominator, enter angle. So there are several factors are there, first factor, second, three factors. So I will separate the angles, angle of S plus 4. So what is the value of S? So here at S equal to 0.75. So S equal to minus 0.75. Okay, fine. Angle of K, okay, let me write the angle later. Tell you angle of K plus J0, fine. Then angle of S, what is S? S is minus 0.75. S is minus 0.75 plus J0, I will write, no problem, no. Right, for this one. Then what is the value of S? I will substitute here minus 0.75. 2 minus 0.75. How much? 2 minus 0.75 means 1.25. Right? 1 point. So angle of 1.25. So S plus 2. 2. What is the value of S? I will substitute minus 0.75. 2 minus 0.75 is 1.25 plus J0. I will write every term in terms of real part as well as imaginary part. Imaginary part is not there. So let me write it as J0 only. So third factor, substitute S equal to minus 0.7. 4 minus 0.75 is 3.25. So angle of 3.25 plus J0 I will write. Okay, now what is the angle of this? 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 We will calculate one by one. So observe here, one thing I want to make you clear. Please concentrate here. This is sigma j omega. If the point lies here, it is plus something, right? So k, for example, k plus j0, k can take any value 1, 2, 3. So 1 plus j0 means imaginary part is not, point will be coming here. Always we measure the angle starting from this. So angle is 0 if any point. So for example, 1 plus j0 or k plus j0, for let me take, k can take any value, k equal to 1, 2, 3, right? So the point has to be lying on the real axis only, positive real axis. If the point lies here, we always measure the angle starting from this positive real axis. So angle is 0. So numerator term, angle of k plus j0, it is 0 degree. So what is the angle of k plus j0? It is 0 degree. The another way is tan inverse of y by x. So this is x plus iy, x plus jy or iy. Tan inverse of y by x, that also you can calculate tan inverse of y by x. So tan inverse of 0 is 0 degree. That is one way. Another way is I will not use tan inverse. Sometimes I will use, but most of the times I will not be using this tan inverse of y by. Just by looking at the point, I will tell you what is the angle. K plus j0. The point comes here, so 0 degree. Next, observe here, minus 0.75 plus j0. Point is coming here, something minus negative, right? So if I measure here, it is plus 180 degree. Always we measure, right? Or if I measure in the clockwise direction, it is minus 180. But always we prefer the angle to be measured in anti-clockwise direction, right? So it is plus 180. So angle of minus 0.75 plus j, minus 0.75, somewhere it will come here, right? Minus 0.75 plus j0. So if I measure the angle, it is plus 180 degree. Next, angle of 1.25 plus j0. 1.25 plus j0 means somewhere it will come here, right? So angle is 0 degree from this. So I am putting dot here, not multiplication, right? So from this I got the angle is 0 degree. From this I got 180 degree is the angle. From this I got the angle is 0 degree. From this, can anyone tell what is the angle? Can anyone tell? 3.25 plus j0, what is the angle of this? 3.25 plus j0, what is the angle of this?
0 degree.
Yes, good, very good, 0 degree, because the point lies on the real axis. From this it is 0 degree. So corresponding I have written here. Okay, 0 degree. Then we should always add the angles, don't multiply the angles. 180 degree plus 0 degree plus 0 degree. So in the denominator I got 180 degree. After adding, we have to always add the angles. So this is angle of g of s into h of s, right? So if I take it to numerator, 0 degree minus 180 degree, finally I will get minus 180 degree. Whether this satisfies angle condition or not? Yes, it is satisfying angle condition, because angle condition is plus or minus odd multiple of 180 degree. I am getting minus 180 degree. So angle of g of s into h of s equal to minus 180 degree. So it satisfies angle condition. It satisfies, it means the point S equal to minus 0.75 satisfies angle condition. So given point S equal to minus 0.75 lies on the root locus, Okay, fine. I hope you understand. So if the point has to be on the root locus, means it has to satisfy angle condition. If it satisfies angle condition, I will say that the point lies on the root locus. If it is on the root locus, means it has to satisfy angle condition. I hope you are understanding my statement, what I am making, right? Okay. Suppose if I get something like this, let me change the ink color. If I get, for example, for any point g of s into h of s, if I calculate the angle, if I get plus 240 degree, so angle condition is not satisfied because it should be odd multiple of 180 degree. 180 degree into 1, 180 degree into 3, 180 degree into 5, 180 degree into 7. So it is not odd multiple. It does not satisfy, right? So angle condition is not satisfied here. So angle condition fails here in this case, right? I hope you are getting, right? Okay, I hope you understood. The same thing has been done here, but I have done here, right? Okay. Okay, next. This is example 8.3.1. What I have done? Example 8.3.1. Okay, for this the solution was given here, but I have solved here in the next slide, blank slide. Next, let us consider instead of s equal to minus 0.5, we will take this point, right? And we'll check next. So consider the system with another example. Consider the system with g of s and h of s equal to k dot by s into s plus 2 into s plus 4. Find whether the point s equal to minus 1 plus j4 lies on the root locus using angle condition. So we will proceed. K divided by s into s plus 2 into s plus 4 and they have given the point whether this point s equal to minus 1 plus j4 lies on root locus or not. They are asking for this point, right? Okay, example, another example 8.3.1. okay, okay, whether this will, once again, what is the angle condition? Angle condition is angle of g of s into h of s is equal to plus or minus 2q plus 1. 2q plus 1 means odd multiple of 180 degree. I read it like this, odd multiple of, instead of always reading 2q plus 1, I will read it as plus or minus odd multiple of 180 degree. This is the angle condition. So we will apply the angle for this. Angle of g of s into h of s at point s is equal to, this point is given, minus 1 plus j4. So angle of k, numerator, I have to apply angle for this, right? Entire thing. So angle of k plus j0 I will write, divided by, next I will apply angle of s. What is s? S is minus 1 plus j4. So angle of minus 1 plus j4. Then next I will apply angle of s plus 2. Okay, what is s? S is minus 1 plus j4. So minus 1 plus j4 plus 2. 2 minus 1 is 1. 1 plus j4. Directly I have simplified and written, because substitute the value of s here, minus 1 plus j4. So 2 minus 1 is 1. 1 plus j4, second value. Then third, s plus 4. Substitute the value of s here, right? Substitute the value of s here, minus 1 plus j4. 1 minute, just 1 minute. Okay, fine. Sorry for the interruption. Next, angle of s is over, angle of s plus 2 is over. Next, angle of s plus 4. What is this s? Substitute s. S is minus 1 plus j4. 4 minus 1 is 3. 3 plus j4. I hope you are getting what I am doing. If any doubts, please unmute yourself and talk to me so that I will clarify your doubts. So substitute the value of s here. What is s? Minus 1 plus j4, right? So 4 minus 1 is 3. 3 plus j4. So calculate the angle for this. So angle for this already know, k plus j0, it lies in positive area, so it is 0 degree. So let me come for this minus 1 plus j4. What is the angle of this, right? I want to calculate the angle for this. So minus 1 plus j4, the point comes somewhere here. Just let me mark it here. Sigma j omega minus 1 plus j4 somewhere here. So this is minus 1 plus j4. So you can observe here the angle is this 90 degree plus something, means the angle lies between 90 degree to 180 degree. So this is 0 degree, 0 degree, 90 degree, 180, 270, right? So the angle lies between 90 to 180. We know that the angle lies between 90 to 180. But just by looking at the point, I cannot. But I can tell the angle lies between 90 to 180. But I cannot tell the exact value, whether it is 100, 110, something I cannot tell like that. So we will make use of tan inverse of y by x. What is y? 4. What is x? Minus 1. So minus. So we will calculate the angle for this. So what I will be getting? Just let me tan inverse of minus 4. Tan inverse of minus 4. So I am getting minus 75. Minus 75.96 degree. Just you observe, I know that the angle should be between 90 to 180, but I am getting minus 75. It is coming in fourth quadrant. Minus 75 somewhere it will come here. So means exactly opposite. I am getting this line, right? Minus 70. The angle is fine. Minus 75, but I want only positive angle. So add plus 180 degree to it. So minus 75, add 180 degree to it. So add 180 plus 180. So I am getting 104. 104.03 degree. Yes, the angle is lying between 90 to 180. So I came to know that it is 104.03 degree. I hope you are getting. Next, we will calculate this angle. Tan inverse of 1 plus j4. So 1 plus j4 means a point will come here. The angle is lying between 0 to 90 degree. I am very much sure it should lie between 0 to 90. So let me calculate tan inverse of 4 by 1. So tan inverse of 4. So I am getting 75. Yes, it is fine. 70 to 90 degree. It is correct. So it is 75.96 degree. So this one, let me separate it like this. Okay, 75.96. This is correct. Next, we will calculate this angle. Third one. So 3 plus j4. 1 to 3 plus j4 means once again it lies between 0 to 90 degree. Let us calculate this. Tan inverse of 4 by 3. Y by x. Tan inverse of y by x, right? So tan inverse of 4 by 3. So 53 degree I am getting. 53.13 degree. So it is between 0 to 90. It is correct, right? So we will write all the angles. Numerator 0 degree divided by denominator 104.03 degree. So you can write within brackets 75.96 degree. Third one 53.13 degree. So always 0 degree divided by, add all the angles, add this plus this, add it, right? So 104.03 plus 75.96 plus 53.13. So I am getting 233.12 degree. If I take it to numerator, 0 degree minus 230. So I am getting minus 233.12 degree. So angle of g of s into h of s, what I got is g of s into h of s for the point s equal to minus 1 plus j4. What I got is minus 233.12 degree. So this is not odd multiple of 180 degree. So this does not satisfy angle condition. Since the point does not satisfy angle condition, so the point s equal to minus 1 plus j4 do not lie on the root locus. Do not lie on root locus. This point does not lie on the root locus. We have proved, right? Okay, something happened. Okay, fine. This point does not lie on root locus. Right? I hope you understood. Yes, I can give any number of points. Yes can be anything, either real, it is real or complex, something like that, right? So we can test whether the point lies on root locus or not. If the point lies on the root locus, means it has to satisfy angle condition. If it does not satisfy angle condition, means the point does not lie on the root locus. Please keep in the mind. Next we will see the magnitude condition next. Okay, angle condition already we have seen, and we know that g of s into h of s is equal to -1 plus j0. This is from characteristic equation. 1 plus g of s into h of s equal to 0. G of s into h of s equal to -1 plus j0. This we know. So apply magnitude on both the sides. Apply magnitude. So magnitude of g of s into h of s equal to magnitude of -1 plus j0. It is under root of x square plus y square. So under root of -1 whole square plus 0. So I am getting 1. So this is the magnitude condition. So magnitude of g of s into h of s at some point, whatever may be the point, is equal to 1. So magnitude condition is magnitude g of s into h of s at any point s which is on the root locus is equal to 1. So this is magnitude condition. Okay, one statement I will make. Please be careful, listen attentively. From this magnitude condition, I can determine the value of k. What is system gain? Right? I can determine the value of k. For example, g of s into h of s is equal to k divided by s into s plus 2 s plus 4. I can determine this value of k by using magnitude condition, right? But if the point s, for example, s equal to minus 0.75, earlier I had given one point, and -1 plus j4 another point I had given, whether they, okay, already the point should lie on the root locus, then only I will go for a magnitude condition in order to determine the value of k, right? If the point satisfies magnitude condition, it doesn't mean that it is on the root locus. If the, I am making one, once again I am repeating, if the point, any value of point s equal to any, right, it may be real number or positive number, real number or imaginary or complex. So if any point s satisfies magnitude condition, this one magnitude of is, it does not mean that it is on the root locus, right? Okay, but if it satisfies angle condition, means it is on the root locus. Please keep in the mind. So we will take this magnitude condition and try to prove, right? Okay, fine. We'll take up this numerical. The same thing, g of s into h of s is given, k divided by this one, and s equal to minus 0.75 is confirmed to be on the root locus. They are already telling that this s equal to minus 0.75 is on the root locus. No need to prove angle condition because they themselves are telling it is on the root locus. Now it is, then they are asking to find out the value of k. What is this value of k? Find out. So we'll make use of magnitude condition and we'll find out. Okay, okay, let me not, don't look at this. Okay, leave this, don't look at this, I'll solve here. So let me change the ink color. So g of s, what is magnitude condition? We want to find out what is the value of k here. So we'll make use of magnitude condition. Magnitude condition. So magnitude of g of s into h of s at the point s is equal to, so minus 0.75, they are given the point, right? Minus 0.75, it is on the root locus, right? S equal to minus 0.75 is equal to 1. So this is the magnitude condition. Call this as equation 1, right? Okay, we will apply the magnitude for this. Magnitude of this. So g of s into h of s is this. G of s into h of s, it is given, k divided by s into s plus 2 into s plus 4. So apply magnitude on both the sides. This one. So let me, I am writing here, magnitude of g of s into h of s is equal to magnitude of k, right? Magnitude of k plus magnitude of s. One by one I am writing magnitude of s. This first. Next, magnitude of s plus 2. Magnitude of s plus 2. Next, magnitude of s plus 4. At s is equal to what? S equal to minus 0.75. Okay. And it is equal to 1. We will make use, it is equal to 1 I can write, but I will take it later. So magnitude of k is k only. K plus j0 if I write, magnitude of k is k only. Right? K plus j0 under root of k square plus 0 square. You know how to find out the magnitude, right? So what is s? S is minus 0.75. So what is magnitude of minus 0.75? It is 0.75. Then next substitute s equal to minus 0.2 minus 0.75. It is 1.25. What is magnitude of 1.25? It is 1.25 only. Then substitute third one. So substitute s equal to minus 0.7. 4 minus 0.75 it is 3.25. So what is magnitude of 3.25? It is 3.25 only. Okay, these are the magnitudes. We have to multiply the magnitudes here. In the angle condition, we have added the angles. Here, don't add them. Don't multiply them. So k divided by, just add them. Sorry, multiply them. 0.75 into 1.25 into 3.25. So 0.75 into 1.25 into 3.25. So I am getting it as 3.046. 3.0468. Okay. And from equation 1, we know that magnitude of g of s and s equal to 1 is 1. So equate it to 1. So what is the value of k? K is equal to 3.0468. Yes. So we have studied two conditions, angle condition and magnitude condition. Why we are using angle condition? To prove that the point lies on the root locus. If the point lies on the root locus means it has to satisfy angle condition. If the point does not satisfy angle condition, it means that the point is not lying on the root locus. That is one thing. Then we are making use of magnitude condition in order to determine the value of k, system gain, right? Okay, 1 minute. So we are using the magnitude condition in order to determine the value of k. I hope you understood. Any doubts, please unmute yourself and talk to me. I hope angle condition, magnitude condition are clear. Yes? Any doubts? Okay, just now we have seen magnitude condition in order to determine the value of k. Next we'll see the graphical method of determining the value of k. One thing we have seen magnitude condition, right? Alternative method is magnitude condition we have used. Magnitude condition. To determine k we have seen. To determine value of k. Next we'll see the graphical method of determining the value of k. Okay, how to find out? This is the formula. K is equal to, I hope you will not understand anything if I read this, but let me read this. K is equal to product of phasor lengths drawn from open loop poles up to a point on the root locus. This is one thing. So it is with respect to poles means P1 into P2 into P3 based on the number and so on it continues, divided by product of phasor lengths drawn from the open loop zeros with respect to zeros up to a point on the root loop. Let me call it as Z1 Z2 into Z3 into and so on. Okay, how to calculate this P1 I will tell you. What is Z1 Z2? Suppose in the G of S into H of S, the numerator will give me zeros, the denominator will give me poles, right? Suppose in the numerator I don't have any zeros, then if I don't have any zeros, I should not write 0. I should take it this term as 1. Denominator. That same thing, if open loop zeros are absent, then denominator in the above expression must be treated as unity. Don't take it as 0. It should be treated as unity if zeros are absent here. Okay, please keep in the mind. We'll take one example and try to understand this formula. Product of phasor lengths drawn from open loop poles up to a point on the root locus. Product of phasor lengths drawn from open loop zeros up to a point on the root locus. With respect to zeros, numerator with respect to poles, denominator with respect to zeros. If zeros are not there, take it as 1. Right? Okay. We will solve this example. We'll consider this. The solution is there, but I will not have a look at this. I will consider only this. Consider g of s into g of s into h of s is equal to k divided by s into s plus 4. S into s plus 4. Is it fine? Find k. Yes, we have to find the k. What is k? For s equal to minus 2 plus j5. Yes, we want to find out the value of k for s equal to minus 2 plus j5. So yes, we can use magnitude condition, but they are asking do by graphical method, right? So using graphical method. So find out the value of k. Okay, we will go. Right, okay. First, we'll how many poles? Let me have a look at the poles. I will observe the denominator. I look at the numerator first. No zeros are there. No zeros. Looking at the numerator, I came to know that there are no zeros. But what about the poles? Poles are there. Poles are located at equate the denominator to 0. S equal to 0. S plus 4 equal to means minus 4. 0 and minus 4 are the poles. Right? These are the poles. And this is the point. Right? This point is given. Right? We want to determine the value of k. Let me draw here. Observe carefully. If any doubts, please clarify your doubts immediately. Okay, at 0, one of the pole is located. And minus 4, somewhere it will come here. Minus 4. This is minus 4. And this is 0. We have located 2 poles. Let me locate this given point. Minus 2 plus j5. Minus 2, somewhere it will come here. Plus j5. Right? So minus 2 plus j5. This is minus 2 plus j5. This is minus 2, right? Minus 2 plus j5. This is plus j5. Corresponding point. Is it fine? Okay. Next, what is k? Product of phasor lengths drawn from open loop poles. Numerator, right? So this is one pole here, located at 0. So from this, let me change the ink color. So from this, I will draw this phasor length corresponding to this point. This is the pole, one of the pole. From this pole, I am drawing this to the given point, minus 2. So let this distance, let me call it as P1. And I have another pole. From this, I will draw the line to this given point. This length will call it as P2. There is no third pole. If it is there, I would have joined it. So, okay, fine. Phasor lengths. There are no zeros here. Suppose let the 0 is there. If I join from, suppose let me assume 0 is located here at plus 2. So I can join it. I will call it as Z1. But here no zeros are there. No zeros. Poles are located. So product of phasor lengths drawn from open loop poles. So P1, P2. So P1 into P2. Divide no zeros are there means take this denominator as 1. Already I have told you. If there are no zeros, take this denominator as 1. So what is this P1, P2? We have to find out. Call this as equation 1. So K is equal to product of phasor lengths drawn from open loop poles divided by product of phasor lengths drawn from open loop zeros. But there are no zeros here. So I am taking the denominator as 1. So what is how to find out this P1, P2? So just let me change the ink color now. So this is hypotenuse, right? Under root of, so this height, what is this? From here to here, it is 5. Right? 0 to 5. This is 5. What is this? Magnitude I am writing 2. Right? So under, if I want P1, under root of 5 square, Pythagoras theorem, 5 square plus 2 square. So 5 is 25 plus 4, root 29. Similarly, calculate P2. So this side is 4 minus 4 minus 2. Total magnitude is 2 only, right? From 4 to 2. This distance is 2. So this side is 2, this side is 5. So under root of 5 square plus 2 square. So it is once again root 29. So using equation 1 implies k is equal to P1 into P2. Root 29 into root 29 divided by 1. So finally it is 29. So k is 29. I hope you are getting. So value of k is 29. Using magnitude condition, you do it using homework I am giving. Calculate value of k using magnitude condition. So you should get the same value, k equal to 29 only, right? So they are done here, k equal to 29. So this is the homework for you people. Calculate value of k using magnitude condition. Magnitude condition, just I will write g of s into h of s. Magnitude at the value of s is equal to, they have given minus 2 plus j5. Minus 2 plus j5 is equal to 1. This is the magnitude condition. Apply magnitude and equate it to 1. Substitute the value of s, and finally k value should be 29. Calculate it. This is homework for you people. Any doubts, you can unmute yourself. Yes, this already okay. This root locus example I will not discuss here. Yes, we will see the rules for the construction of root locus. Very important. Totally 8 rules are there. So we will learn the rules one by one, right? Just like while the block diagram reduction technique, there were about 11 to 12 block diagram reduction rules, right? After learning all those 10 to 12 block diagram reduction rules, we were able to simplify the block diagram. Here we have set of 8 rules are there. So using these 8 rules, we will be in a position to construct the root locus. After constructing the root locus, then we have to judge whether the system is stable, unstable, or marginally stable. All those things we have to comment on the stability. So first, our aim is to construct the root locus. Before constructing root locus, we should be knowing the rules how to construct the root locus. So we will see the rules for the construction of the root locus, right? Rule number one. What rule number one? The root locus is always symmetrical about the real axis. Yes, you can observe here. This is one example. This is the real axis. So above part and below part, they are symmetrical, mirror images, right? So you can see here, right? So above part and below part. So yes, no need to tell anything. The root locus is always symmetrical about the real axis. If it is not symmetrical, means that is not root locus. Please keep in the mind. We have done, if we draw the root locus and if there is no symmetry about the real axis, then you have gone wrong somewhere while drawing the root locus. That is the meaning, right? So the root locus is always symmetrical about the real axis. Then we'll take up the rule number 2. I'll change the ink color. Rule number 2, right? So I'll not go through all these things. It gives information about branches. So rule number 2 will give information about branches. What are the branches? I told already. Yes, there is a pole here. From this pole, the branch will move like this. It moves in the upward direction. This is one branch, right? Then next, another branch from this pole. The pole is here at -1. It starts here. It moves symmetrically in the downward direction. This is another branch, second branch. The third branch, I'll change the ink color. The pole is located here. It starts and moves towards infinity. So 3 branches are there. So rule number 2 will tell how many. It gives information about the branches. Means how the branches will start, where they will start, where they will go. This is moving towards infinity. This is moving towards infinity. This is moving towards infinity, right? So how many branches are there? How they will move. So that is all about rule number 2. So we'll see this rule number 2, right? Okay. Please keep in the mind, rule number 2 gives information about the branches. Okay. We have the open loop transfer function g of s into h of s. The numerator will give me the poles, right? So let me denote it by capital P, number of open loop poles. Then denominator will give me zeros, the number of open loop zeros. Let me call it as z and p. Okay, I will take one by one. Case 1. Case 1 where p is greater than z, right? So let me take the example. For example, here I have taken p is greater than z means, let me write it here. Let me take red ink only. So p is 4, for example. Number of poles are 0, zeros is 1. So here case 1 is p is greater than z, right? P is greater than z. So how many branches are there? So always it is given by, so which is greater? P is greater, z is less, right? So n is equal to p. It is 4. So n means the number of branches. N means the number of branches. Yes, there are 4 branches as per this, right? N equal to 4 branches because n equal to p. What is this p? It is 4 here. So the number of branches, 4 branches are there. Okay, we came to know that there are 4 branches. Then where they will start, always the branches will start from open loop poles, right? Here you can see here there is pole located at 0, -1 and -3. Always the branches are starting from here. This is the pole, the branch is starting here. Another pole, the branch is starting here. Another pole, the branches. Always the branches will start from open loop poles. And you can observe here, this is p greater than z. How many poles are there here? 0, -1, -3. 3 poles are there. Are there any zeros here? For example, in this example, no zeros. So how many branches are there? P minus z. Sorry, n equal to p. That is equal to 3. 3 branches are there. This is one branch, green color. It is moving like this. Another branch, second branch. Then third branch, it goes like this. I hope you are getting p greater than z, right? So 3 branches are there. Always the branches will start from open loop poles. And another one thing, since there are no zeros, if there are any zeros, the branches will try to terminate on the available zeros. Since there are no zeros, this branch will start here and it moves towards infinity. This branch is starting here and it is going towards infinity, just endless. This branch is starting here and it is moving towards infinity because zeros are absent. If any zeros are there, one of the branch will terminate on the available zero, right? Okay, just we'll see for the example, right? So here I have taken example. Here p is 4, z is 1. So I came to know that 4 branches are there, right? So one of the 0 is there, means one of the branch will start from the total of 4 poles. Maybe let me take the 4 poles. One is 1 at 0, -1, -2, -3. These are the 4 poles. Let me take, right? And one of the 0 is there. Let me take it at uh, okay, let it be 2 or something like that. Let me, right? 4 poles are there, and always one branch will start from this 0, -1, -2. Always the branches will start from open loop poles, and since there is 1 0, one of the pole, one of the branch will terminate on this available 0, and remaining 3 poles will move towards infinity. I hope you are getting. I came to know that there are 4 branches, out of which 3 branches, 4 branches are there. All the 4 branches will start from the available open loop poles, but one of the branch will terminate on the available 0 because there is only 1 0, right? It will terminate on this. And what about the remaining 3 branches? They will start and they will move towards infinity. The same thing has been read. 4 branches will start from the locations of the open loop poles. Out of this, only one will terminate at the available finite open loop 0 location. The remaining branches means p minus z. 4 minus 3, 1, 3. Remaining 3 branches will approach towards infinity. So this p minus z will give me the number of branches which are moving towards infinity. This is for case 1. Next we'll take case 2 here. Case 2 means, let me take example. P is, for example, 1, z is 4. Here p is less than z, right? Second condition is p is less. The first condition is p is greater than z, that we have seen. Second condition is p is less than z or z is less than z is greater than p, one and the same, right? Okay, in this condition what will happen? The number of branches n is equal to, which is highest? Z is highest, so z. So it is 4. Once again in this case 4 branches are there, right? Okay. Always the branches will start from open loop poles, I told, right? So only one pole is there. So one of the branch will start from this pole. What about remaining 3 branches, right? They start from infinity because there is no pole. They start from infinity, and since the 4 zeros are there, always the branches, please, I will make one statement here, please all of you listen. Always branches will start from available open loop poles, and they always try to terminate on the available open loop zeros. Always they will try to terminate on the available open loop zeros, right? If there are no open loop zeros, they will try to move towards infinity, right? Okay, you can observe here only one, but branches are 4, so only one of the branch will start from one of the available pole. Remaining 3 branches will start from infinity, right? And all the branches will terminate on this available open loop 0 because 4 zeros are there. So 4 branches are there. One of the branch will start from the available open loop pole. Remaining 3 branches, they will start from infinity because there is no pole here. They are but they will terminate on the available zeros. In this case, second case, the same thing they have written here, p equal to 1, z equal to 4. So number of branches is 4. The number of branches, so 3 branches will start from infinity, while one branch will start from location of open loop pole, and all 4 branches will terminate at available 4. The same thing whatever I have said. I hope if any doubts are there, you can ask, or else we will take up the numericals and I'll try to make you understand. Third case. So p greater than z condition we have seen. P less than z, then p equal to z. Suppose p is equal to z. What will happen? It is very much clear. So the number of branches is equal to p are equal to z, one and the same, because p equal to z, right? So p equal to z, right? Okay, let me take one example. The poles are 2, zeros are 2. If there are 2 poles and 2 zeros, so the number of branches are 2. And where they will start, where they will terminate? Since 2 poles are there, the 2 branches will start from the 2 available open loop poles, and they will terminate on the available 2 zeros. They'll start and terminate, start at open loop poles and terminate on open loop 0. The same thing has been told here, right? Okay, so 3 cases are there. So this rule number 2 will speak about will give information about branches, how many branches are there, from where they will start, where they will terminate, where they will go, all these things, right? So three cases: p greater than z, p less than z, p equal to z, we have seen, right? The next we'll see the rule number 3. Okay, anyhow I'll continue because still I'll have time, I can continue. So 11:4, let me continue. I want to finish this topic till rule number 5. I will cover rule number 3. Okay, this rule number 3 will speak about the existence of root locus on real axis. Rule number 2, it gives information about branches, that we have seen. Next, rule number 3 will speak about the existence of root locus on real axis. For example, let me take this root locus. See here, this is the real axis, right? This is the real axis. This entire thing is real axis. So where the root locus is from section 0 to -1. Yes, 0 to -1 root locus is. From -1 to -3 there is no root locus. From -1 to -3 it is not a part of root locus. You can observe from -3 to till -infinity, -3, -4, till -infinity, the root locus is there. But in this section, -1 to -3, root locus is not there. Means that rule number 3 will speak about in which section of the real axis. This is the real axis. In which section the root locus exists. How to find out, that we are telling, right? Only the root locus on the real axis, not root locus other than real axis, like this. So on the real axis, in which section, 0 to -1, -1 to -3, -3 to and so on, in which section of the real axis the root locus exists. I hope it is clear. Let us solve few problems, but before that we have to understand this rule number 3. A point on the real axis lies on the root locus if the sum of the number of open loop poles and the open loop zeros on the real axis to the right hand side of this point is odd. Okay, what is the meaning of this? I will tell you. You can observe here. Okay, this pole is located at 0, another pole is at -1, another pole is at -3. Okay, I want to find out whether from section 0 to -1, whether the root locus is not there or not, in between 0 to -1. Let me locate one point here. Let me locate one point. Let me locate this point. Let me call this as point A between location 0 to -1. To the right hand side of this, to the right hand side of this point A, I will count the number of poles and zeros. So if I count, no zeros are there, only one. It is odd. If it is odd, means yes, the section 0 to -1 is a part of root locus. Next, from -1 to -3, I will take another point B. And on the right hand side of this, I will count the number of open loop poles and zeros. So this is one pole, this is one pole. So 2, I am getting the count as 2, means totally 2 poles, right? So this is not, I have to get odd number. So I am getting even number. So this 0, -1 to -3 is not a part of root locus. -1 to -3 is not a part of root locus. From -3, I will take another point C here, and I will count the number of poles and zeros. Pole 1, 2, 3. I am getting odd, means from -3 to -infinity, it is a part of root locus. The same thing has been told here. A point on the real axis, I will read once again, please try to understand. A point on the real axis lies on the root locus if the sum of the number of open loop poles plus sum of the number of open loop zeros on the real axis to the right hand side of this point is odd. This is very important, it should be odd. Okay, we will take up this example here. 1 minute. Yes, we'll take up this example. G of s into h of s is equal to k into s plus 1 into s plus 4 divided by s into s plus 3 into s plus 5. What question there? Using rule number 3, find on which section of real axis the root locus exists. We have to use rule number 3, existence of root locus on real axis. Yes, how many zeros are there, where they are located? Zeros are located at s equal to numerator. Observe the numerator and equate them to 0. S equal to -1, -4. So how many zeros are there? Capital 2 zeros are there. So and poles are located at s equal to, I equate the denominator term to 0. S equal to 0, s equal to -3, s equal to -5. So how many poles are there? 3 poles. right? So just we'll try to locate these poles and zeros first. Sigma j omega. So the poles and zeros I will try to locate. At 0, one of the pole is there. Poles are marked by cross and zeros are marked by this circle, right? This is the notation. Zeros by circle, poles by cross. At 0, -1, -2, -3. Let me take it here, -3 and -5. I have located poles at 0, -3, minus. Next I locate zeros. Zeros are located at -1. Here, one of the 0 is there. This is at -1. I am locating here. At -4, it will come here. Yes. Next I'll change the ink color. In which section? Yes, I have located all the poles and zeros. This is the right in the S plane. This is the pole zero diagram because location of poles and zeros. 3 poles are there, 1, 2, 3 and 2 zeros, right? Next, using rule number 3, I want to find out in which section on the real axis the root locus exists. I will take the section first 0 to -1. Let me consider point A here. Between section 0, let me consider. To the right hand side of it, I will look at and I will check how many. I will add all the poles and zeros. Only one pole. It is odd. So this is part of root locus. 0 to -1. Root locus exists here. Root locus exists. Next, I will take section from -1 to -3. Right? -1 to -2 also I can take. But let me take section from -1 to -2, -2 to -3. This means nothing is there, right? So let me take one point here. Consider this point B. Anywhere, right? And to the right hand side I will count 1, 2. Since there are even number of poles and zeros, so no root locus exists from this section, from here to here. Means -1 to no root locus. No root locus exists. -1 to -3, there is no root locus. Next, let me shift that point here. -3 to -4. Let me consider point C here between section -3 to -4. To the right hand side I will count 1. This is one pole, this is 1 0, so 1 plus 1 plus 1, totally 3. Add all the poles and zeros to the right hand side of it. 1 2 3. I am getting odd, so -3 to -4 is a part of root locus. Yes, root locus exists. So root locus exists. Root locus exists between section -3 to -4. Then I'll shift the point between -4 to -5. Let me call it as D. To the right hand side I will count all the poles and zeros. 1 2 3 4. So it is odd. So -4 to no root locus. No root locus exists. No root locus exists. Next I'll shift the point from -5 to infinity. Anywhere I can take. Let me take point E. To the right hand side I will count 1 2 3 4 5. Odd means from -5 to -infinity. Root locus exists. Root locus exists. I hope you are getting. Root locus exists. Simply I will write RL. RL means root locus exists. From -1 to -3 there is no root locus. There is no root locus here. Here there is no root locus, right? So you can write NRL, no root locus. If you want, you can write like this, NRL. No root locus means NRL, right? I hope you are getting. If any doubts you can ask. So rule number 3 will speak about the existence of root locus only on real axis, not on imaginary axis, only on real axis, right? The same thing has been given here and I have told you, right? Next, we'll take up this example once again, another example. Yes, g of s into h of s is equal to k divided by s square into s square plus 2s plus 2 s plus 3 s square plus 2s plus 2. Okay, something has been written myself. Okay, so find sections on real axis which belongs to root locus. Yes, we'll try to s square plus 2s. Okay, what happened I don't know. Plus 2 into s plus 3. Sorry. Okay. Okay, using rule number 3, find out on which section the root locus is. Yes, How many poles are there? How many zeros are there? There are no zeros. Look at the numerator. There are no zeros. No zeros. How many poles are there? Just look at the denominator. So s square, right? This is s square, yes. So 2, 2, 4, 4 plus 1. 5 poles are there. From this I will get 2 poles. From s square I will get 2 poles. From this one. So 2 plus 2, total 5. Highest order is 5. So poles are located at s equal to s square equal to 0, 2 0. So 0 comma 0 are the poles. So let me take this first. S plus 3 equal to 0 minus 3. So let me solve for this. S square plus 2s plus 2. Its roots. Just I have the roots here. Just I will calculate the roots from the calci. You will get the roots as I think this is minus 1 plus or minus j. Minus 1 plus or minus. Or else let me calculate the roots for this. So equation. I will go to degree. So a is 1. B is
Excuse
2.
me, sir.
Yes, tell me. Yes, tell
Sir,
me.
one of the term is missing in numerator, sir.
One of the numerator. Let me just check it. Yes, s plus 2 is there. Yes, I have missed it. Thank you. Thank you very much. Thank you. S plus 2. Who is this? Okay, let it. Numerator. Yes, zeros are there. I have missed this numerator term s plus 2. Okay, fine. So zeros. This is wrong. How many zeros are there? 1 0 is there. Z equal to 1. So what are zeros are located at? Zeros are located at. Thank you. Located at s equal to minus 2. Yes, 1 0 is there. Okay, we'll calculate the roots of this. So let me calculate. A is 1, B is 2, C is 2. So the root is minus 1. Imaginary part is plus j. Another root is minus 1. 1 minute. X1, x2 is minus 1 minus j. Minus 1 plus or minus j. Minus 1 plus j, minus 1 minus j. So totally 5 roots are there. Let me locate these roots. Sigma j omega. Let me change the ink color. You can also make use of colors in the exam, no problem, right? Okay, let me look at the poles. 0 0. One of the pole and another pole is located same there only. So I am making double mark here. 2. You should be identified. Don't draw the thick, right? There are 2 poles located 0. Minus 3, one pole is minus 1 plus j. So let minus 1 is here. Plus j. Somewhere it will minus 1 plus j. Minus 1 minus j. This is a minus 1. Next, minus 3. Minus 3. So I located 5 poles here. 3, right? 5 poles are over. Next, I look at zeros. S equal to minus 2. 0. Yes. I located all the poles and zeros in the S plane. Next, I want to find out existence of root locus. Let me change the ink color. First, from 0, this is 0. 0 to minus 1. Whether the root locus exists or not, I will consider one point between the section 0 to minus 1. Right? So, to the right hand side, if I count 2 are there, means this is not 0 to minus 1 is not a part of root locus. Yes, I hope you are getting. Then I'll shift the point from minus 1 to minus 2. Yes, I'll consider point here, somewhere here. To the right hand side, I will count. So you can see here, you can neglect this complex conjugate poles. Or else, if you consider also, no problem. See here, 2, 1, 2, 3, 4. Here 2 poles are there, 3, 4. You can neglect also because anyhow, if they will not affect. So you can neglect or else you can count, no problem. 2 plus 2, 4. So once again, minus 1 to minus 2 is not a part of root locus. Next, shift the point from minus 2 to minus 3 here. Just count here. 1, 2, 3, 4, 5. Yes, this section minus 2 to minus 3 is a part of root locus. Next, I'll shift the point here. So I'll count all the poles and zeros. 1, 2, 3, 4, 5, 6. Means this minus 3 to minus infinity is not a part. Only the root locus exists between the section minus 2 to minus 3. Only root locus exists here. In other parts, it is not there. I hope you got it. Any doubts you can ask. The root locus exists only in this section, minus 2 to minus 3. Right? The same thing has been written here. Okay, I don't know what is happening here. Multiple copies are written here. Okay. If I draw in the next slide, it is coming here also. I don't know how it had come. Whatever I have written here, it will come here. Okay, let it be. Not worry. Rule number 4. It is coming on all the slides. What happened? It is coming on all the slides. Okay, let me save it. What is happening? I'm not getting. It went. Okay. Let it be. I hope you understood. Right? It's coming in previous slides. Rule number 3 is over. What shall I do? Let me close it and open it. Okay, fine. Rule number 3 I have understood. Let me start with rule number 4. Okay, let me recall. Rule number 1, what does it say? It says that the root locus is symmetrical about the real axis. And rule number 2 speaks about the number of branches. How many branches are there, where they are moving, how they are moving, all those things. Right? Then in that rule number 2, there are 3 cases: P greater than Z, P less than Z, P equal to Z. And rule number 3 will speak about the existence of root locus on the real axis. Next, we will consider the rule number 4. Rule number 4. It speaks about asymptotes. Okay? It speaks about the asymptotes. What are asymptotes? Already I have told you. Once again I will tell you. Right? So let me take the same example. See here, this branch is moving here and it is moving in this direction. Who is telling you go in this direction? Why it should move only in this direction? This asymptote. Here I have located, this is the asymptote. Here, this one. This is, let me change the ink color. This is the asymptote. This is the angle 60 degree it is making. Theta 1 equal to 60 degree. And another asymptote is here. Theta 2. 180 degree. 60 degree, 180 degree. This is 180 degree. Next, another asymptote is here. Theta 3 equal to 300 degree. This is 300 degree. Okay, this asymptote is telling for this branch move in this direction, and this asymptote is telling move in this direction. This branch is moving, move in this direction, and this asymptote is telling the branch should move in this direction. So these asymptotes are nothing but the guidelines for the branches which are moving towards infinity. All these branches are moving towards infinity. From here it starts and it is going towards infinity. Here it starts, it is going towards infinity. Here the branch will start and it is going towards infinity. So finally this rule number 4 will speak about asymptotes. So what are asymptotes? Asymptotes are the guidelines for the branches which are moving towards infinity. And how to calculate the angles of asymptotes, I will tell you. Right? Okay, the formula to calculate the angles of asymptotes is 2q plus 1 into 180 degree divided by p minus z. So plus or minus is not there. Please keep in the mind. Right? So it is just 2q plus 1 into 180 degree divided by 2q plus 1 is nothing but odd multiple. So q can take any value 0, 1, 2 till p minus z minus 1. This is very important. P minus z minus 1. Right? So q can take any value 0, 1, 2 till p minus z minus 1. P is the number of open loop poles, Z is the number of open loop zeros, right? So asymptotes are always symmetrically located about real axis. You can see here, just now I shown. Yes, if I take the real axis, it is symmetrical, right? One of the, right? So it is symmetrical about real axis, up and down. Yes. So how to calculate angle of this equal theta equal as angle of asymptotes. Angle of asymptotes. What are asymptotes? TOTES. Asymptotes are the guidelines for the branches which are moving towards infinity. And how to calculate the angle of asymptotes? That theta equal to odd multiple of 180 degree. 2q plus 1 into 1 into 180 degree divided by p minus z. P minus z will give you the number of branches which are moving towards infinity. Right? Denominator. And I had shown you the angle here. Theta 1 is 60 degree. Theta 2 is 180 degree. Theta 3 is 360 degree. I have calculated by using this formula only, this formula, right? So we will see next one numerical based on this. Next, rule number 5. Today I will wind up for rule number 5 and I will solve one numerical and I will wind up the today's lecture after rule number 5. I hope you understand rule number 4. Rule number 4 always speaks about the asymptotes. What are asymptotes? Asymptotes are the guidelines for the branches which are moving towards infinity, and how to calculate the angle of asymptotes by using this formula theta, right? Okay, next we will speak about rule number 5. We will speak about rule number 5. What happened? Okay. We'll speak about rule number 5. Okay, rule number 5 speaks about centroid. What is centroid? I will tell you. Just I will go to this diagram back. Yes, this asymptote. I have to take one point. From this I have to measure angle. Theta 1 is 60 degree. This point, this centroid is minus 1.33. Means this centroid is always located on the real axis. I have to, how to calculate this centroid? That is very important. So, centroid, it is the location for to measure the angle of asymptotes. Means theta 1 is 60 degree, theta 1 is 180 degree, theta 3 is 300 degree. From this point I will measure the angle. So it gives the location of the asymptotes on the real axis. The centroid will give the location of the asymptotes on the real axis. This is the real axis, right? So what is centroid? So just I'll read out this whatever thing. Now only the angles of asymptotes are not sufficient, but where the asymptote should lie in the S-plane, where they should be located, is equally important, and it is given by the centroid. Location of asymptotes in S-plane is given by this rule, and that is nothing we call it as centroid. CENTROID. All the asymptotes intersect the real axis at a common point. They are intersecting there, right? So at a common point known as centroid, and centroid is denoted by sigma. And how to calculate this centroid sigma, that point? So we have calculated here, it is sigma equal to minus 1.33. How to calculate this? We'll see. Sigma is equal to summation of, this is summation symbol, summation of real parts of poles, only real parts, observe here, not the imaginary parts, real parts of poles of the open loop transfer function g of s into h of s minus the summation of the real parts of zeros of the open loop transfer function g of s into h of s divided by p minus z. This is sigma, right? Okay. Then next, please don't put any message because I cannot go to the chat box and see your messages. You can unmute yourself and talk to me so that I can clarify your doubts, because I cannot go back and switch to that window and see the messages in the chat box. I got some beep sound, so I'm telling. Okay, let it be. Unmute yourself and talk to me if for any doubts. So centroid. So how to calculate centroid? Sum of real parts of the open loop pole, poles of g of s into h of s minus summation of sum of real parts of zeros of the open loop transfer function g divided by p minus z. P minus z will give me the number of branches which are moving towards infinity. And centroid is always real. It cannot be imaginary. It always lies on the real axis. It can be either negative or positive. Centroid is always real. It may be located on negative real axis or positive real axis. And one more thing, it may be or may not be the part of root locus. Right, you can observe here, minus 1.33. So minus 1 to minus 3, there is no root locus. This point centroid may be a part of root locus or may not. It is not mandatory that it should be a part of root locus, right? Okay, I hope you came to know rule number 4 and 5. Yes, we will see this question bank question is there, right? For g of s into h of s equal to this k divided by s plus 1 into s plus 2 plus j2, s plus 2 minus j2. Calculate the angles of asymptotes we have to calculate and centroid, and draw the sketch. Draw the sketch indicating the same. Sketch indicating the same. Yes. Okay. Before solving this problem, I want to list out rule number 1. What does it say? Can unmute and tell you rule number 1. What does it say? Rule number 1. Unmute yourself and talk to me. We will brief all the 5 rules. Then I will solve this problem. Please. What does rule number 1 say? The root locus is always symmetrical about real axis. Symmetrical about real axis. What does rule number 2 speak about? Rule number 2. It gives information about branches. Then rule number 3. It tells the existence of root locus on real axis. Existence of root locus on real axis. At least tell rule number 4. Just now we have seen. What does rule number 4 speak about? Rule number 4. It speaks about asymptotes. Rule number 5, it speaks about centroid. Asymptotes are the guidelines for the branches which are moving towards infinity, and centroid, it is the location on the real axis where the asymptote should be located, right? It is on the real axis and it is real. Okay, just we'll take up this numerical for g of s into h of s. Let me go to the next slide. Yes, I have a blank slide here. G of s into h of s. This is the last numerical of today's class. Okay, it's already 11:30. I know it. Just I'm extending the class. K divided by s plus 1 into s plus 2 plus j2. Next s plus 2 minus j2. I hope it is correct. Calculate angle of asymptotes and centroid. So asymptotes and centroid you have to calculate. So asymptotes and centroid. Asymptotes and centroid. So we'll calculate this and we'll also draw the sketch. Sketch also, right? So first, how to calculate angle of asymptotes? So the formula is given by, okay, before writing the formula for asymptotes and centroid, let me write down how many zeros are there, how many poles are there. So how many poles are there? Just look at the multiply. Highest power of s is 3, means 3 poles are there in the denominator. So where they are located? So equate them to 0. S equal to minus 1 is one of the pole. So equate this to 0. So what I will be getting? Minus 2. You take that side. Minus 2 minus j2. From this minus 2 plus j2. So these are the location of the poles. Next, how many zeros are there? In the numerator there are no zeros. Z is 0. So no zeros. Okay, we have seen the poles and zeros information. Next, we will write the formula for asymptotes. Angle of asymptotes. Angle of asymptotes. So the formula is given by theta is equal to 2q plus 1 into 180 degree divided by p minus z. You should be knowing this. And value of q runs from 0, 1, 2 and so on till p minus z minus 1. So first let us calculate p minus z minus 1. What is p minus z minus 1? P minus z minus 1. So what is p? 3. What is 0? Z is 0 minus 1. So what is p minus z minus 3 minus 1 is 2. So q can take values 0, 1, 2, only this much. 0, 1, 2, only these three values it can take. Because till p minus z minus 1. P minus z minus 1 is 2, right? So for q equal to 0, calculate theta 1. Right? 1 minute. Yes. Okay, sorry for the interruption. I thought some people have called, you people only, and some other call. Okay, I'll not attend all those calls. Okay, let me finish the class first. Okay, for q equal to 0, substitute q equal to 0 here. So 2 into 0 plus 1, 180 degree, right? This 0, 2 into 0 plus 1. So 1 into 180. So 180 degree divided by, what is p minus z? P minus z. Let me write p minus z here. So what I'll be getting p minus z? P is 3, Z is 0. So I am getting P minus Z as 3. So I will substitute 3. So calculate 60 degree I am getting. Then Q equal to 1 I will substitute. So calculate by substituting Q equal to 1. So calculate theta 2. So substitute Q equal to 2 here. 2 to the 4. 4 plus 1, 5. 5 into 180 degree. 5 into 180 degree. So I am getting 900. Divided by P minus Z is 3. So 3 to the 6, 3 3 is 9. So 900 divided by 3. So 300 degree I am getting. Somewhere I have done wrong something. Just let me check it. Q equal to 1. If I substitute, what will happen? Q equal to 1. Q equal to 1.
Sir, it's 540 divided by 3.
That only. Somewhere I have, that only I am searching. So Q equal to 1 means 202. 2 plus 1, 5. 5 into 18. 5 into 180 degree. I am getting 5 into 180 degree as 900. No. Why it is 540? 0, 1, 200, 2 plus 1, 3. Sorry, 3 I am getting. I was taking this as 5. 2 plus 1 3, 3 into 180, it is 540, correct. 540, it is not 900, 540. Please don't make the mistake what I have made. 540 by 3 divided by 3, so I am getting 180 degree. Okay, thank you. For q equal to 2, okay, q equal to 2, theta 3, angle first for theta 1, theta 2, theta 3 I am calling, right? So substitute q equal to 2, 2 to 4, 4 plus 1 5. Now it is 900 by 3, so I am getting 300 degree. Okay, we have calculated angle of asymptotes. Over. Next, asymptotes is over. Next we will calculate centroid. Centroid, that we denote it by sigma. What is the formula? Sigma is equal to sum of real parts of open loop poles. Real parts of poles of open loop zeros. This is the formula, right? Sum of real parts of poles minus sum of real parts of zeros divided by p minus z. So sum of real parts of poles, right? Real RP means real parts of poles of open loop minus sum of real parts of open loop zeros divided by p minus z. Okay, we will calculate what is, so we will observe only real parts of poles. So minus 1, minus 2, minus 2, only this real part. I will not consider this imaginary part. So add all these poles, real parts of poles, right? Minus 1, minus 2, plus of minus 2 is minus 2 only. I am adding, right? So minus 1, plus of minus 2, plus of minus 2. Next, this is over. Minus, open bracket, real parts of zeros. So there are no zeros. So 0. There are no zeros. Divided by p minus z is 3. So calculate this. How much I will get? 2 to 4 plus 1 5 minus 5 by 3. 2 plus 2 4, 4 plus 1 5. 5 minus 5 by 3. 5 divided by 3. So I am getting minus 1.667. So we have calculated centroid and we have calculated angle of asymptotes. Then we have to sketch. So this is very important. Observe here. We'll sketch it. This is one of the question in the question bank, right? For you people. Sigma j omega. So first I look at the centroid. This is 0 minus 1.667. It will come here. Let me take it here. Minus 1.667. Okay. This is the centroid sigma. This centroid I have located. Next, angle of asymptotes. Theta 1 is 60 degree. From this location of centroid, I have to draw the angle 60 degree. So angle will come. Let me change the ink color. 60 degree. So take the protractor and measure, or roughly you can draw. So this is theta 1. Theta 1 equal to 60 degree. This angle is 60 from here to here. Next, theta 2 is 180 degree. It will come here 180 degree if I measure. Theta 2 equal to 180 degree from here to here, right? Just observe here, from here to here 180 degree. Next, 300 degree. 300 degree means it will come like this. It has to be symmetrical, no? Right? So theta 3 equal to 300 degree. You can observe here, from here to here, if I take this line 270 plus this 300, right? 180, 270 plus something angle 300, right? I hope you are getting. This is 60 degree. This angle is 180. This angle is 300. Measure it, right? Okay, roughly I am drawn. So this is the sketch indicating the asymptotes and centroid. I hope any doubts you can ask. We'll stop here the today's lecture. I'll stop recording.